Inside a healthy artery, blood surges at extreme velocities, subjecting the vessel walls to a shear rate of up to 800 reciprocal seconds. When that vessel ruptures, this high-pressure liquid faces a critical physical deadline. It must transition into a localized structural solid in a matter of seconds. This is the biological paradox of hemostasis. The body must rapidly construct a physical plug strong enough to stop hemorrhage, yet restricted enough to ensure that the clot doesn't propagate and trigger a fatal systemic thrombosis. To understand how this equilibrium is maintained, we look back to the 19th century, when Rudolf Virchow defined the requirements for blood clotting. He categorized the pathophysiological mechanisms of thrombosis as a triad of 3 distinct vulnerabilities: altered blood flow, a hypercoagulable state, and direct damage to the vessel wall. Hemostasis functions as a highly localized, tightly controlled temporal mechanism engineered to preserve systemic equilibrium and prevent runaway clotting. To execute this defense, the body deploys an architectural sequence broken into 4 distinct stages. Stage 1 is immediate vasoconstriction. The injured vessel physically clamps down to drastically reduce local blood flow to the breach. Stage 2 is primary hemostasis. This involves the rapid activation of platelets to build an initial temporary plug over the defect. Stage 3 brings in secondary hemostasis, characterized by the localized generation of thrombin to weave a permanent structural fibrin mesh. Finally, Stage 4 is fibrinolysis, the methodical breakdown of that clot as the underlying tissue repairs itself. This 4-step baseline architecture provides the map for identifying exactly where the system collapses in life-threatening conditions, like disseminated intravascular coagulation or hemophilia. When the endothelial wall tears, subendothelial collagen is instantly exposed. This triggers a neurovascular reflex. Platelets release vasoactive amines and thromboxane A2, forcing the vessel to constrict, slowing hemorrhage. Under extreme shear stress, von Willebrand factor unspools, binding tightly to the collagen. Once anchored, this von Willebrand factor acts like a net, catching circulating platelets as they tether themselves to it using specific GP1b9V surface receptors. This tethering triggers a rapid intracellular alarm. The platelet structurally transforms from a smooth disc into a spiky amoeboid shape. It then degranulates, dumping potent signaling molecules like ADP and serotonin into the local environment to recruit additional platelets. This internal signaling also activates a second set of receptors, GPIIB/3A, which allow the clustered platelets to bind with circulating fibrinogen, linking them together into an aggregated mass. This primary platelet plug is a vital patch to stop bleeding. However, it lacks the structural integrity to permanently withstand arterial pressure without chemical reinforcement. Reinforcement begins with secondary hemostasis. When tissue factor is exposed by the injury, it binds with clotting factor 7A, forming the initiation complex. This triggers a localized cell-based coagulation cascade, operating in 3 distinct phases: initiation, amplification, and a massive wave of propagation. The goal of this exponential cascade is to generate a massive burst of thrombin. Thrombin is the ultimate effector enzyme. It acts like biochemical scissors, cleaving soluble, free-floating fibrinogen into insoluble strands of fibrin. These fibrin strands quickly polymerize and cross-link with one another, wrapping around the temporary platelet patch to form a hardened, permanent biological concrete. But while this clotting storm rages at the breach, the adjacent, uninjured endothelial cells are actively working to survive it. They continuously secrete substances like prostacyclin and nitric oxide. These molecules form an invisible antithrombotic shield, shutting down platelet aggregation and halting the cascade the second it tries to expand past the injury line. Normal secondary hemostasis relies on these explosive procoagulant reactions being restricted in space by the antithrombotic defenses of the surrounding healthy tissue. When this system breaks, the results go in opposite directions. In hemophilia, the cascade fails during amplification. A primary platelet plug forms, but without sufficient thrombin, there is no stable fibrin mesh, resulting in structural failure and continuous bleeding. Modern hematology combats this through rebalancing therapies. By targeting and inhibiting the body's natural anticoagulants, like tissue factor pathway inhibitor or antithrombin, clinicians can remove the biological brakes, forcing the impaired cascade to proceed and generate a stable clot. But the inverse scenario happens in the ICU during severe trauma or sepsis. The massive inflammatory response physically shreds the protective endothelial glycocalyx lining the blood vessels. Instead of a localized breach, the blood is suddenly exposed to a systemic flood of tissue factor, along with pathogen and damage-associated molecular patterns. This triggers a hyperactivation of the entire coagulation system. Hundreds of thousands of microscopic clots form simultaneously, choking off the microvasculature and rapidly exhausting the body's natural anticoagulant reserves. This is disseminated intravascular coagulation. It presents a terrifying clinical paradox. The patient bleeds profusely from every line and puncture site because every available platelet and clotting factor has already been consumed in a microscopic crossfire. Because the mechanisms are physically distinct, their failures look completely different at the bedside. Primary hemostasis defects manifest as superficial bleeding, appearing as tiny purple petechiae spots. Conversely, secondary hemostasis defects fail to build structural concrete, causing massive deep tissue bleeding, like expanding muscle hematomas. The entire hemostatic system exists on a constant precarious seesaw. Procoagulant drivers continuously push against the natural anticoagulants and the fibrinolytic action of plasmin. By accurately identifying the physical presentation of a bleed, a trained clinician can deduce exactly which side of the biochemical seesaw has broken. Returning to the disseminated intravascular coagulation paradox, we see this physiological failure directly reflected in the lab results: a prolonged PT and aPTT, a plummeting platelet count, and rapidly rising D-dimer levels. These lab findings show the coagulation factory is running at maximum capacity, but depositing its output in the wrong locations. The immediate intervention is often to support the patient with fresh frozen plasma, restocking the consumed coagulation factors to stop the bleeding. But there is a critical caveat here. Without actively treating the underlying infection or trauma driving the endothelial injury, infusing replacement factors only provides fresh fuel for the pathological clotting to continue. Mastering hemostasis requires looking past the surface symptoms. It demands trusting objective lab assays and applying first principles physiology to guide highly targeted, life-saving resuscitations in the intensive care unit.